Okay then, hello YouTube, welcome to my YouTube channel. Today we're going to be solving the second problem from the CSES introductory section, which is called as missing number. So it says you're given all numbers between 1 to n except 1, and your task is to find the missing number. So the first input line contains an integer n. Okay, then let's type long as read. Okay, it's all positive, so I'm going directory slash d. And then apart from that, it says the second line contains n minus 1 numbers. Each number is distinct and it's between 1 to n, and n is inclusive. Okay, so we can have a vector, an array over here, and since all are positive numbers, and a of, let's say, n I less than I plus plus 5, and then so I want to get all numbers, and it's going to be n minus 1. So yeah, and then our job is to print the missing number. Okay, so the most important thing about this problem actually is the constraint. So if you see the constraint, it can go maximum up to 10 power 5. The time limit is 1 second. Okay, so um, just to let you know, 1 second typically means let's say 10 power, it's gonna work up to an input of 10 power 8, input size of 10 power 8 in a sense. Let me just make it in a much clearer way. Maybe I meant yeah. So what I'm trying to say is, let's say by this time limit, they mean you can perform 10 you can perform operations for an input size of maximum 10 power 8, and the reason behind this stuff uh, is as follows. So let's say we have a modern CPU processor which might be like 3 gigahertz or something. So let's say 1 gigahertz to clock cycles. It's approximately 1 gigahertz is approximately 10 power 9 clock cycles per second. Okay, so the reason why we when we write something like, let's say we write this particular for loop for int I is equal to 0, and let's assume n is something like almost 10 power 5. So inside here we only have one operation, but this is primitive operation itself. Like apart from this, we might have sometimes addition, subtraction. We might have like multiple operations like a of I plus equal to 1, and a of I minus equal to 1, and so on. But these are not one operations. These operations, if you go underneath, there might be assembly instructions happening to execute these operations. This one is currently in a high level language, but behind the scenes there might be a lot of stuff happening. So due to this particular reason, let's say we have in every step there are like some 5 to 8 assembly instructions involved. So in that case, it would become 8 into 10 power 8, and no matter whatever, how many ever assembly instructions we have, with this safe number 10 power 8, we can be sure that it's always going to be less than this 10 power 9. So in that way, it will always be able to execute all the your entire code in for that input size in 1 second time limit. So I hope this made sense. And due to that reason, here we have 10 power 5. So 10 power 5 is way below 10 power 8. right? So because of this thing, it is possible for us to go through each and every element in the array once, because we can go through all 10 power 5 elements. We do have the luxury thanks to the constraints. So do this thing. What I'm gonna do is over here, let me have something called as sum, which is initially 0, and sum plus is equal to a of I. Okay, so I do have the sum, and now there's a formula which the sum of first n natural numbers is n into n plus 1 by 2. So this is the sum of the first n natural numbers. I will do a proof by induction on this later in this video, but let me just first finish this code, and then we can do the proof. So then let me say un32/t total sum is equal to n into n plus 1 and into n plus 1 by 2. Okay, this is going to be the total sum. And finally, the answer is just going to be total sum minus the sum. Okay, so the logic is, look, it's simple. So let's say we have n is equal to 5. So the first 5 natural numbers are 1, 2, 3, 4, 5. And he says the second line contains n minus 1 number, where each number is distinct and is between 1 and n. N is also inclusive, so it's gonna be 1 comma n. Okay, let's say in this case 1 comma 5. So let's say in the second thing I have number 1, 3, 4, and 5. So if I add this thing, the sum is gonna be what? Sum is gonna be 5 plus, okay, it's gonna be 13. Okay, and here if you use the formula n into n plus 1 by 2, so it's gonna be 5 into 5 plus 1, which is 6, which is 30. I can just write for you 5 plus 1 by 2, which is equal to 30 by 2, which is equal to 15. So now if you do 15 minus 13 is going to be equal to 2, right? So 2 was the missing number. If you see over here, we don't have 2, we just have 1, 3, 4, 5. So that's the reason where by using the formula and thanks to the constraint, we can go through each element of the array once and add it. We're gonna get the answer. And let me just try to compile this now and show it to you. Missing number, .cpp. No error, thankfully. If I have 5 and 2, 3, 1, 5, we get the answer 4. And now let me try submitting this thing and see what's gonna happen. CSES, YouTube, introductory. This is missing number. Okay, there are wrong answers. So this is also very good for us. It's good learning for us. So what is this? Is 10 power 5 something. So it expected something and then it got a very huge number. And same thing over here. For bigger things, it's getting very huge number 1. Okay, almost 10 power 9. Possibly some overflow problem. If you remember, like it's similar to the problem we faced last time. So what's happening is, let's say this n is 10 power 5, right? So 10 power 5 into 10 power 5 is gonna go to what? 10 power 10. And as I told you in the last video, this gonna be 2 power 32 minus 1, which is approximately gonna be 10 power 9. So it can only hold, UN32T can only hold values up to 10 power 9. So that's why when this goes to, let's say if n is equal to 10 power 5, so 10 power 5, n into n is going to be 10 power 5 into 10 power 5, which is going to be 10 power 10. So due to this thing, 10 power 10 is greater than 10 power 9. So our thing cannot actually hold it, and because of this thing, we might face overflow errors as we faced over here. So what I'm gonna do now is I will just change mm, these two things to 6040, 64-bit. With this, it can easily hold values up to, I think, 10 power 18. So yeah, thanks to the constraint, we can be certain that it is not going to exceed this value. So as the maximum is 10 power 5, and now if I, even the answer has to be maybe 6040, and now if I run this, okay, if I gonna submit this thing again, let's see what's gonna happen. Missing number. Okay, again it's wrong answer, so there might be some other problem. It was not overflow, it's giving a very big value. So they do some mistake over here, n into n plus 1 by 2. The formula is correct, but okay, it didn't overflow, but okay, the formula is wrong. Okay, let me just see what's happening over here. Total sum is n into n plus 1 by 2, and sum. So number is so massive that total sum is giving some error over here. Mm, so let's say if maximum is 10 power 5 into 10 power 5 is gonna be 10 power 10, and 10 power 10 by 2, it should not be a problem because okay, no, it cannot be more than this. Vect int is fine. N also is fine with that, but okay, I understood this thing. Listen, guys, what is happening over here is this one, right? This one is 32T. So this 64T is just a storage place. But what is happening is in the intermediate registers, which we have over here, N is still UN32T. So N is still like, how to say, it's like it can only hold up to N. I'll just write down over here so it can be better. So look, the storage place, the final storing place is UN64T. But n is still UN32T, right? Because we declare it on top as that. So what's happening over here is when we multiply two UN32Ts over here, this 2 1 n into n, the intermediary is gonna still get stored in UN32T register. The final register where it's gonna get stored would be the UN64T. But by that time, this two things, if you multiply 10 power, let's say it's 10 power 5, right? So 10 power 5 to 10 power 5 would be 10 power 10. But UN32T cannot actually store this particular value. So in that case, we might get the wrong thing stored in the intermediate register, and that is exactly the problem we were facing over here. So what we can actually do over here is we can try changing this thing to 64/t, and yeah, maybe this will definitely work, I'm sure. So now if I add missing number, Yeah, see, it got accepted. So yeah, I think this was very good learning for us. We did face problems and we try to learn. And now, apart from this, I will just show you a small, I think, induction proof for the sum of the first n natural numbers. So I'm saying that the sum of first n natural, um, okay, then one second. I will just open and I'm just saying that sum of the first n natural numbers is n into n plus 1 by 2. So how do I prove this? Let's take a base case for 1. So 1 into 1 plus 1 is going to be 2 by 2 would be what? Would be 1 only. So the first, yes, the first natural number is 1. So natural numbers are actually like this. They go from 1 comma 2 all the way till, and they start from 1. So the first natural number is sum is of course 1. So it's true for our base case. Yeah, and then the next step is the hypothesis step, where let's say for some n is equal to k, we assume it to be true. So for n is equal to k, it's going to be k into k plus 1 by 2. Okay, this is true. We assume it's true, right? Then we have to prove that it's true for k plus 1. So for k plus 1, it would be k plus 1 into k plus 2 by 2, right? So this is what we have, but now it's up to us to prove this particular thing. So how we're gonna prove it is, let's say we have a natural number 1, 2, 3 all the way till k, and then it's gonna have k plus 1, right? So what is the sum of let's say then yeah, so we have this 1, 2, 3 all the way till k, and then we have the k plus 1 as well. We are gonna add everything, sorry. So 1 plus 2 plus 3 plus all the way till k, and then plus k plus 1. Okay, it is supposedly should be equal to this thing. So we already know from our hypothesis that if it's up to k, let me just write over here, it's gonna be like this. So it's equal to k into k plus 1 by 2. Okay, I think I might write this in whiteboard if it's gonna be better for you guys to understand. So it's gonna be like this thing, yeah. So it's gonna be like this, k into k plus 1 by 2, right? This thing, this term over here, the last term, right? So up to k, it's k plus 1, and it's gonna be plus k plus 1. Okay, it's gonna be like that, plus k plus 1. So we have this denominator 2 over here, so but this thing has no denominator, so what I'm gonna do is just gonna like multiply it by 2, and then yeah, it yeah, then this what is gonna happen. So now we have the common denominator over here, so if we try to multiply and get it done, what's gonna happen is this thing gonna become k square plus k plus 2k, so plus 3k So yeah, it's gonna be k square plus 3k plus 1 all divided by 2. Okay, and then we have this thing from here which says k, which prove that, sorry, this one, k plus 1 into k plus 2 by 2. So can we try to expand this thing? Yeah, so let's take this term over here. So this thing is equal to k square plus 3k plus 1 and all divided by 2. Okay, and what is this term which we had to prove? So it was just yeah, it was like this, like, a second, I just want to check if it's visible or not. Okay, so if you write over there, that term was k plus 1 into k. I'm really sorry for the handwriting, guys. I will try to get better at the whiteboard. Using the whiteboard, k plus 1 into k plus 2 and all divided by 2, yeah? So what? Okay, this thing is not visible, so okay, I'll just do one thing. I'll just try to zoom to it inside maybe. Okay, sorry, then 1 minute. Let's try to okay, so this k plus 1 into k plus 2 and the denominator is going to be 2. Okay, uh, just let the denominator be 2. I will write it later on, but if you multiply this thing, it's going to be k square plus 2k plus 1k plus 2, right? And sorry, I made one mistake over here. This one is whole into 2, so this one is going to be plus 1 into 2, so it's going to be 2. Yeah, so it's going to be what, k square plus 2k plus 2, right? So k square plus 3k plus 2, and this thing also is going to be the same thing. It's going to be this thing, k square plus 3k plus 2, and in the denominator we're going to have the 2 term. So yeah, then if I go over here, this thing is k square plus 2, sorry, and this also is equal to k square plus 3k plus 2 by 2. So since both the things are equal, we have proved that yeah, since both are equal, yeah, we have thus we have just proved it. We have proved it's true for k plus 1. So this is how we proved by induction that the sum of first natural numbers is n into n plus 1 by 2. Okay, yeah, it's gonna be equal, this thing gonna be, oh my god, so let's copy this thing. Okay, but anyway, I just hope you get the idea of how we prove by induction the sum of the first n natural numbers. And then yeah, that was it for this video. We were able to submit the answer. I hope you did learn something from this video, and I will see you again with another video. Thank you.